sorry. The next talk, let me just look at my, okay, so the next talk is the best student paper. And this is a presentation that is pre-recorded. It's a presentation by John Napp. And I think that is indeed, we are recording now. So I think the presentation will be shared in a moment. So let me just check something. Oh yeah, there it comes. Yeah, so this is efficient classical simulation on random shallow 2D quantum circuits. So John Napp and Rolando La Placa and Alex Dalzell got the Best Student Prize for this work. And John will be available on Slack to answer questions and also in the Q&A the last 5 minutes of the presentation. So I think you can start the slides now. Oh, he's actually there or not? Oh, it's the recording. Okay, sorry. Yeah, go ahead.
Thank you for coming to this talk. I'll be talking about some joint work together with Rolando La Placa, Alex Dalzell, Fernando Brandão, and Aram Harrow about algorithms for random shallow 2D quantum circuits. So first I'll give a bit of motivation for why we are interested in this problem. So I think a good place to start is this quote by Richard Feynman from the early 1980s, in which he points out that nature is quantum, not classical. So if we want to simulate nature, it makes sense to make the simulation itself quantum. And the sentiment and the underlying assumption that interesting quantum systems are generally hard to simulate classically is one of the driving motivations of the field. So it makes sense to try to understand how much we can actually push back against this sentiment and try to find interesting examples of quantum systems and quantum circuits which actually do admit efficient classical simulations. And as a more immediate motivation, you probably have heard of Google's recent claim to have performed some quantum computational task beyond the capabilities of classical algorithms. And this claim rests on a hardness assumption regarding the hardness of simulating random quantum circuits. So to better understand the strength of their claim, it makes sense to better understand the complexity of simulating random circuits. But I should note that their claim rests on the hardness of simulating deep random circuits in 2 dimensions, whereas our results are for shallow circuits. So our results do not refute their claim in any way. So now I'll define the actual computational task we'll be studying here. And this is called random circuit sampling, and it corresponds to the task that Google's proposal is built on. So looking at the cartoon in the bottom of the screen, we imagine that we start with an array of n qubits represented by the blue dots. And then we apply some random circuit consisting of some number of layers of 2 local Harrow gates, followed by measurements on all sites in the computational basis. So looking at the cartoon on the bottom, we can imagine these red lines represent the first layer of gates, second layer, third layer. And actually, this pattern of gates that I just implemented is known as a brickwork architecture, and it will be the main architecture I'll be focusing on in this talk. So after we perform those gates, all of the sites are measured, represented by the red X's. Okay, so what is the actual computational task? So the computational task is to at least approximately generate samples from the appropriate output distribution, call it D sub C, corresponding to the realized random circuit C. And this should be done with high probability over the realization of random circuit. So now I'll mention a couple of known hardness results for this problem. So if we assume the non-collapse of the polynomial hierarchy, which is believed to be the case, then following a result of Turhal and DiVincenzo, we know that at least for classical algorithms that make error that's exponentially small in some sense, the sampling task is worst case hard. So this means that if we have any efficient classical algorithm for sampling, it cannot generically work on all random circuit realizations. And due to a much more recent result of Rolando et al., we also know that for an alternative computational task of computing specific output probabilities rather than sampling, that task is hard not only in the worst case, but also in the average case, meaning if we have any efficient classical algorithm for computing output probabilities, that algorithm will fail on some significant fraction of random circuit realizations. So one might wonder if the above 2 points might already point to the hardness of the computational task that we're actually primarily interested in, random circuit sampling. And note that random circuit sampling corresponds to approximate average case sampling. And one implication of our work is that the above points should not necessarily be viewed as evidence for the hardness of random circuit sampling on their own, because we can construct examples of random circuits for which the above hardness results apply, but nonetheless, random circuit sampling is classically easy via our proposed algorithms. But I should note for the specialists that the examples that we construct like this do not satisfy an anti-concentration property. So now I will summarize our results. So we propose 2 classical algorithms for random circuit sampling, which are applicable for constant depth 2D circuits. And while we propose 2 algorithms, I'll just focus on one in this talk. So we have 2 classes of results, provable results and also conjectures supported by numerical and analytical evidence. So on the provable side, as I mentioned previously, we can show that there exist certain 2D depth 3 random circuit architectures for which the previous hardness results apply, but nonetheless, random circuit sampling is tractable using our algorithms. And this is nice in that it's provable, but unfortunately, it only works for certain architectures. So we want to understand the complexity of this problem more generally. And to this end, we conjecture that random circuit sampling is classically tractable for sufficiently shallow circuits more generally using our algorithms. And I'll talk more later about what I actually mean by sufficiently shallow. We also conjecture that there's an interesting catch here, namely that our algorithms experience computational phase transitions from polynomial time regimes to inefficient exponential time regimes as the 2D circuit depth or the local Hilbert space dimension exceed some critical values. And these critical values you can think of as constants that generally depend on the details of how the architecture is specified. Okay, so moving on, now I will give you a description of how one of these simulation algorithms works. So the high-level idea is that we'll do some sort of 2D to 1D reduction, and then we'll simulate the 1D process with matrix product states. And if you're familiar with measurement-based quantum computing, some of these ideas might look familiar. So I'll illustrate this with the brickwork architecture I introduced before. So recall that we have this first layer of gates, second layer, third layer. And then recall that we have measurements on all sites, but without loss of generality, we can imagine that the measurements of column 1, the leftmost column, are performed first, and then those of column 2, then column 3, 4, 5, until all of the columns are measured. And the strategy of the simulation algorithm is going to be to first simulate the measurements of column 1, and then column 2, etc. Okay, so how can we do this? So we want to start by simulating the measurements on column 1. So to do that, we can simulate the application of gates which lie in the causal cone of column 1. So that is, we can simulate the application of gates which can influence the density matrix corresponding to column 1. So in this example, this would be these gates that I've sketched in the bottom half of the screen. So we simulate those gates, and then we simulate measurements on column 1. Now we move on to column 2, and we simulate the application of gates which lie in the causal cone of column 2, but have not previously been applied. So we need to simulate the application of these gates in this example, and then we simulate measurements on column 2. And we just keep iterating this logic until we have simulated measurements on all of the columns. So this idea is fairly simple, but the complicated part is trying to argue and understand why this sort of reduction might yield an efficient classical simulation. So I'll point out that the simulation algorithm, you can see progresses through some sequence of states. So if there's L sub 2 columns originally, we can think of in the bottom half of the screen, there's essentially an effective 1D dynamics involving a one-dimensional quantum state evolving for L sub 2 time steps. And the goal is to now simulate this effective 1D process. So why might we hope that that is simulable? Well, for this, we can turn to an observation of Vidal, namely that for such a process, if the process is only lightly entangled in some sense, then efficient approximation using matrix product states might be possible. So matrix product states are essentially one-dimensional tensor networks, which are good at approximately describing low entanglement states. Okay, so now why might we hope that the entanglement is low in this effective 1D dynamics? So I'll talk more about that on the next slide, but here I'll just note that for some special cases of architecture, we can just formally show that indeed the entanglement in the effective 1D process is very low, and efficient approximation via matrix product states is possible, making only small error. All right, so now I'll talk about why we might hope more generally that this algorithm, or rather this approach might work. So thinking about the previous slide, recall that there were these alternating rounds of random gates and measurements on some subset of sites in this effective 1D dynamics. And now I'll point out that this sort of process looks very similar to these so-called random unitary and measurement processes, which have been studied in a very large number of recent works. So let me describe what these are. So the idea here is that we start with a one-dimensional quantum state. So looking at this picture, we think of time as going from left to right, and we start with a 1D state on the left-hand side, and then we apply alternating rounds of local random gates and weak measurements performed on all of the sites. And there's an interesting question here about how the entanglement behaves in such a process, because the unitaries will tend to increase the amount of entanglement in the system, while the measurements will tend to destroy entanglement. But since they're weak measurements, they don't destroy all of the pre-existing entanglement necessarily. And the interesting conclusion from this line of recent work is that there appears to be an entanglement phase transition in such a process driven by parameters like the measurement strength and the local dimension. So in particular, it appears that the entanglement transitions from an area law phase to a volume law phase as the measurement strength is decreased or the local dimension is increased. And if you're not familiar with what area law and volume law refer to, you can just think of area law as referring to low entanglement and volume law as high entanglement. And also the existence of this phase transition appears to be robust with respect to specific details as to how the model is actually defined. And this is interesting from our perspective because the effective 1D dynamics that we end up with, as on the previous slide, looks quite similar to these sort of processes. And in particular, there's an interesting heuristic correspondence between the depth of the 2D circuit that we want to simulate and the effective measurement strength in the effective 1D dynamics that the simulation algorithm tries to track. So this correspondence gives some indication that we might potentially see a complexity phase transition for our algorithm from an efficient regime to an inefficient regime as the depth and local dimension are tuned. But this is just a heuristic correspondence, so we do additional numerical and analytical analysis to better understand how the algorithm behaves. So now I'll say a little bit about numerical implementation. So this figure at the top here is showing how different Renyi entanglement entropies behave in the effective 1D dynamics corresponding to brickwork architecture. So in particular, it's plotting essentially the average amount of entanglement entropy across the, a cut that goes halfway, that bisects the 1D state. And it's looking at how that tends to behave as a function of the side length. And you can see the plot is indicating that there's no noticeable dependence of these entanglement entropies on the system size, which is indicative of an area law for the entanglement. So getting a little bit more specific, we simulated, focusing on the brickwork architecture, we simulated sizes up to 400 by 400. And I should note that this brickwork architecture of size 400 by 400 is classically intractable using previously known circuit simulation algorithms that we're aware of. And we were able to do this on a laptop with small simulation error. And we know that the error is small because the algorithm actually has a nice property of being self-certifying in the sense that it's able to measure how much error it is incurring. So that gives us confidence that the error is indeed low. So that shows that the algorithm can indeed be quite efficient in practice. As for asymptotics, we looked at how various entanglement properties behaved as the system size is increased or as the effective 1D dynamics progresses. And the analysis here indicates that indeed the algorithm remains efficient asymptotically for the architectures we considered. And also we studied a toy model to better understand the behavior of the entanglement. And the toy model predicted entanglement behavior, which was consistent with what we saw numerically. And the toy model also suggests that the algorithm is indeed efficient asymptotically. So finally, I'll say a little bit about another analytical tool that we use to understand the performance of this algorithm. And this is via a mapping between random circuits and classical statistical mechanical models, which has been studied in other recent works as well. So how does this mapping work? So the idea is that we can associate a Harrow random unitary with two classical spin variables. And this mapping is made possible via Harrow integration formulas. So when we do this mapping for all of the unitaries in the original circuit, we end up with some classical statistical mechanical model. And the nice thing about this mapping is that certain entanglement properties of the original quantum circuit are directly related to physical properties of the associated classical StatMech model. So these pictures show what happens when we apply this mapping to our shallow 2D circuits that we're interested in this work. So the left-hand picture shows a more zoomed in output of the mapping involving only a few random unitaries, and the right-hand picture shows a zoomed out view after the mapping has been applied for the entire circuit. And the takeaway from the right-hand picture is that when we do this mapping, we end up with a quasi two-dimensional stat-mech model, which is icing-like in some ways. And the interesting thing about this mapping is that we find that there is a correspondence between the phase of the statistical mechanical model and also the amount of entanglement present in the effective 1D dynamics that our algorithm aims to simulate. So in particular, we find a correspondence between a disordered phase of the stat-mech model and an area law phase for the entanglement, and also an ordered phase of the stat-mech model and a volume law for the entanglement. But I should note that that these area laws and volume laws are with respect to certain proxies for the entanglement entropy that the stat-mech model is able to access. Unfortunately, the stat-mech model isn't able to access the usual notion of entanglement entropy, so we have to study these proxies instead. So thinking about this brickwork architecture I introduced before, we find that it has an associated stat-mech model that is in a disordered phase, which implies an area law for this proxy for the entanglement entropy that I don't have time to precisely define here. Also, finally, if one increases the qubit dimension or increases the depth of the original quantum circuit, this corresponds to an increase in the effective interaction strength in the associated stat-mech model. So if you're in a disordered phase, that will push the stat-mech model closer to an ordered phase. And eventually we expect a phase transition in the stat-mech model when the local dimension or the depth becomes sufficiently large, which in turn corresponds to a phase transition for these entropic quantities in the effective 1D dynamics. All right, so now just listing some open questions. Obviously, a very interesting and important question is, what about deep 2D random circuits? Can our conjectures be proven rigorously? Also, it would be interesting to understand if Monte Carlo studies of these stat-mech models that I mentioned on the previous slide can be used to understand properties of the algorithm, like its runtime. And in this talk, I focused only on noiseless circuits, but it would be interesting to understand what happens to these algorithms in the presence of noise. Also, in the volume law phase for the entanglement entropy, there's a question of whether the simulation algorithm that I described might still perform better than other known exponential time algorithms, even though the runtime in this case will be exponential time, not polynomial time. And we expect this could be the case, especially when one is close to the phase transition point. And it would also be interesting to see if we might be able to find some continuous time version of the results that I've described. Thanks for listening. Thank you for coming to this talk.
Thank you. Are you on, John? Yes. Okay.
Yes.
Hi. Okay.
Hi.
So I see you already have answered some questions on the Slack channel. Perhaps I can ask a brief question. You mentioned about noise. So can one integrate that in this map to the stat-mech model? Or depending on what, perhaps maybe easy polarizing channel or something?
Yes. Yeah, we're still kind of thinking about this, but I guess, so for example, if say we have like some dephasing noise, then this can be naturally incorporated in this stat-mech mapping and can be sort of understood as a weakening of the interaction strength. So for example, for dephasing noise, we'll get these stat-mech models that are sort of closer to the disordered phase for a given depth and local dimension. So yeah, so in this way, noise can be sort of introduced naturally. But yeah, for more general sorts of noise, yeah, we haven't thought about it too much. Yeah.
Okay, thanks. Let me pick up a question from the audience from Seva Caribbean. Apologies if this is naive, but how does your algorithm compare regarding direct tensor network simulation methods for this setting?
Right.
Well,
so
what is direct tensor network? Okay, yeah, sorry, go ahead.
Yeah, I guess, well, sort of the naive exact thing to do would be to, yeah, just do, so the tensor network, these tensor network algorithms are related to the tree width of the underlying graph. So for these sort of 2D architectures we're considering here, if you say it's like an or square root n by square root n square grid with depth d, then we would expect the runtime of the naive tensor network contraction to scale like exponential in square root n times depth. Yeah.
Right, and this maybe also relates to another question that somebody asked about how this works for general low degree interaction graphs. Then
yeah, so I guess
the 3D composition.
Yeah.
And so on.
Yeah, I guess I'm not sure if I totally understand the question, but yeah, from the way I understand it, I don't see a way to naturally apply our algorithm here because we sort of crucially rely on this reduction to the 1D dynamics. And yeah, so I don't see how that would naturally carry over in this other setting.
Right, but if the 1D is a tree, you are still okay, no? Or is that correct?
Yeah, I guess you would need some, if you have some notion of like spatial locality, then that might make sense.
Yeah.
Yeah, I guess I'm not sure if the question was asking about like spatially local low degree graphs or more generally.
Yeah, it seemed to be more general. Let me. Here is a question, maybe the last one. Oh, yeah. So it's a question by Mikhail Osmaniak. What can be said about the StatMech model if one uses a discrete gate set?
Yeah, so I guess, so this StatMech model, it's sort of a second moment related mapping. So if your gates formed a unitary 2 design, then things should carry over as before. But for for more general discrete gate sets, I don't see a way to immediately carry it over, but I haven't thought about this.
Okay, thanks. Okay, anyhow, I think we're going to wrap up because then we'll stay on time. Thanks very much for answering the questions. And I think also after the session, there is a round table and you can ask more questions and discuss with John. Thanks.
That's great.